All right, well, welcome to another lecture. This lecture is ostensibly on temperature, but we're also going to talk a little bit about heat and this thing called thermal expansion. Objects expand and contract. They get heated up or cooled down, increase temperature, decrease temperature, stuff like that. Yeah, so let's do it. Okay, so what is temperature? Well, for us and for the sort of atomic picture, looking at nature and matter is made up of atoms, and those atoms are very tiny and they're just jiggling around all the time. Temperature is essentially, it's a measure of how much all those atoms are moving overall. It's sort of like the average amount of movement of all of those atoms. More specifically, it's the measure of the average internal energy within any material. So, for our purposes, you could really just think about it as, if on average the molecules are moving, or the atoms that are making up the material are moving, jiggling about more, or moving around faster, that's a higher temperature. If they're moving around less, or jiggling a little bit less, on average, it's a lower temperature. If you recall in the last lecture about gases, the picture of gases I showed you had all of the atoms just flying around in different ways, and I pointed out how the speed of them was indicated by those arrows. Some of them are moving faster, some of them are moving slower, all these random directions on average, or a lot of them are in the middle-ish somewhere. So that's another way of thinking about the average internal energy is sort of like the average speed of all of those atoms, right? Some are going faster, some are going slower, but on average, they're somewhere in the middle. So temperature is a measure of that average energy, that overall sort of motion. So we could imagine the difference between something as cold and hot, like a solid, right? So remember, a solid is just atoms that are sort of stuck and not able to move more than jiggling around within the confines of a structure. So for a solid, like a crystalline solid here, everything's nice and laid out in these rows and columns. When the solid is cool or cold, the atoms are all jiggling around, but they're not jiggling around a whole lot, right? Versus if you increase the temperature in some way, you increase the temperature of that material, each one of those atoms is moving around more, and because of that increased motion, they tend to spread apart, right? They need more room to actually move around because they're moving around more. Same sort of thing happens in liquids, where when the liquid is cold, the atoms are moving around each other. It's liquids, they're free to move around each other, but they're not overall moving super fast, maybe, on average. And that, as opposed to if you heat up a liquid, then each one of those atoms on average is moving faster, and they move around more overall. And again, that more amount of motion means there's generally more space between the atoms because they need more room to move around. And finally, with a gas, exact same thing, low temperature, gas molecules all move around on average, it's average-ish speed, some faster, some slower. But if you increase the temperature of that gas, at average speed goes up, so each one of those is generally moving faster and faster. And the same idea holds. They need more and more room to move because they're moving more and more, so the volume tends to increase as well. So let's look at a little animation of this. So this is just a very simple diagram of like a gas. Maybe there's two colors, so maybe the gas is two different kinds of gas. Maybe it's like air. Maybe it's O2 and N2 or something like that, right? And in this little animation, we have the slider on the bottom where you slide down from cool to hot. And what you notice as you move from hot to cool is everything is moving less overall, right? And also, since it's moving less, it needs less space, right? Versus when you heat it up, everything starts moving faster and faster and faster, and it needs more space to move around. Something that you also might notice in this animation is whether it's cold or whether it's hot, again, there's no one speed that any of them are moving. Some of them move faster, some of them move slower. But what we're worried about, or what really tells us what the temperature overall of this gas would be, is its sort of average speed that all these things are moving, or each of them is moving. Cool, so a bit more about temperature then. In a maybe more day-to-day sense, temperature is just a measure of how warm or how cool something is, how hot or how cold it is. Funnily enough, it's rather important that in physics we say that temperature is something you can measure with a thermometer. There appears to be no real upper limit to temperature, meaning that gases or liquids or solids, the atoms that are making up a material, seems like you could just move faster and faster and faster. It'll probably all become plasma at some point. There's all so much movement and so much energy. But there doesn't really seem to be an upper limit on temperature. However, there is very much a lower limit on temperature. So the lower limit is the state where we end up cooling things down, reducing the temperature so much that there would be no motion at all. Right? Because remember, temperature is just a measure of the average amount of motion. So if you go down further and further and further and further, eventually there's just no motion. Atoms have stopped entirely. And that would be zero, or what we call absolute zero in the temperature. Right? That is a definite lower limit because you can't have less than no motion. And in fact, it may be, I believe, at least so far, it's a limit that we can't really reach anyway. And just to give you a little bit more info about different ways we measure temperature, so just like we can measure distance in feet or in meters or in yards, there's different ways of measuring temperature, different scales to measure temperature in. The one we're most familiar with here in the US is Fahrenheit, where in each of these scales it's useful to have some particular points, and usually those points of reference are sort of the freezing and the boiling point of water. Those are usually good reference points. So in Fahrenheit, water will freeze at 32 degrees Fahrenheit. And this is also technically assuming we're at regular atmospheric pressure. Then that's where water freezes. Water boils in Fahrenheit at 212 degrees Fahrenheit. Kind of odd numbers, but there's some other areas where maybe Fahrenheit make more sense, having to do with body temperature and freezing of the salt and water mixture. But in science and in the metric system, in most of the rest of the world, they don't use Fahrenheit, they use a scale called Celsius. So Celsius is much more defined by the freezing and boiling points of water, where water freezes at 0 degrees Celsius, water boils at 100 degrees Celsius. And body temperature is right around 37 degrees Celsius. Beyond just, if you get into, there's certainly more technical, detailed physics sort of areas, thinking about temperature more. It turns out that even Celsius is not necessarily the best scale or most useful scale in sort of an absolute sense, because in an absolute sense there is a zero. There's a real zero, which is zero atomic motion, and that sort of makes more sense from a physics perspective to be the zero of our scale. So for this final scale we have called the Kelvin scale, or an absolute scale, where zero atomic motion is 0 degrees or 0 Kelvin. And it turns out Kelvin and Celsius or Kelvin was designed then so that it had the same amount of temperature change as Celsius does. So one change 1 degree Celsius, change 1 degree Celsius is equivalent and equal to a change of 1 Kelvin. So these scales are equivalent, and or the units in each of these scales, the Kelvin and Celsius, is equivalent. So that on the Kelvin scale, 0 degrees or freezing, 0 degrees Celsius is about 273 Kelvin, and then 100 degrees above that, 373 Kelvin is water boiling. Yeah. So I don't need to, memorize this or know too much about this. It's just a useful reference point in understanding how we define and measure temperature. So just an example of something that kind of maybe gets you to think a little bit more about what the scales of temperature that we use, is that, say, nitrogen, for example, nitrogen gas will become a liquid at minus 320 degrees Fahrenheit. Right? So that's one reason why liquid nitrogen is used to cool things, do cryogenic cooling, or that kind of level, or if you need something cooled down very, 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 very cold, liquid nitrogen is a great way to do that. You just dump something in liquid nitrogen. But even though that's extremely cold, that's still 130 degrees Fahrenheit warmer than absolute zero, right? Warmer than 0 Kelvin. So things that might be, think about being really cold, there's still a lot of atomic motion going on there. Right. So when thinking about temperature and the motion of the atoms that sort of define what the temperature of an object is, it's important to keep separate or distinct the idea of the sort of total amount of energy in a material versus the average amount of energy in the material. So remember, the average internal energy in a material is what we call essentially the temperature. The total amount of energy that's in internal energy in a material, that could vary, right? And it depends on how much the material there is, right? So just to reiterate, the difference between something like a total and an average, whereas this example was much better suited when I actually was talking to a group of students in a classroom. But if you can imagine a classroom full of college students and how much money each of them has on them, in a class of 20, 30 students, maybe it's something around $1,000, maybe less, a few $100s at least, probably, maybe. But in general, the total is just the total amount of money that's in the room, right? Whereas if we were to look at what the average amount of money per person in that room was, it'd be much less. It might be $20, or maybe $10 even, right? So very big difference between the total amount of something versus the average. And again, the temperature of an object is a measure of the average internal energy, not the total amount of the internal energy. Right? So an example of the difference for temperature would be, I could have a big bucket of water, I could have a couple gallons of water, and I could have like a small teacup of water, right? Both of them can be at the same temperature because on average, the atoms that make up the water in the bucket and the water in the cup, on average, they have the same amount of energy. But in total, if I were to look at the total amount of energy, there's much more energy in the bucket because there's just a lot more atoms that make up the water in the bucket. Right? So same temperature, meaning same average internal energy, but different total energy. So let's compare maybe a little more detail, say a total energy versus, next I'll look at average energy. Right? So if we were to think of what the total internal energy is in any material, like water or iron, right? The total energy is essentially, it depends on how much motion each of the atoms has and how many atoms there are, right? And also what kind of atoms they are. So the total internal energy is going to depend on the temperature of the object, it's going to depend on the mass, meaning the amount of atoms that make up that object, and the material, what kind of atoms they are, what elements or molecules, things like that. So comparing, say, 3 different materials or objects, substances, at the same temperatures, we see that their total internal energy varies quite a bit. So for instance, water, if you have a kilogram of water, right, you have a certain amount of atoms of water, and it's at a temperature of 300 Kelvin. Remember, that's not a very great temperature, that's still below boiling. But the total internal energy is something like 1 million joules, 1.2 million joules. And remember, joule is a measure of energy, right? That's how we measure energy. So just 1.2 million joules. Versus, if you have a kilogram of iron, also at 300 degrees Kelvin, same temperature, same amount of material, but different kind of material, iron versus water, H2O, the total internal energy in that kilogram of iron is only going to be about 120,000 joules, right? So 10 times less. And finally, if you compare that to a single gram of iron, so same at 300 Kelvin, you get same temperature, same material, but just much less mass, 1,000th of the mass. 1,000th of the mass actually means we're just going to straight have 1,000th of the energy, total internal energy, right? So 1 gram of iron at 300 Kelvin, total internal energy there, about 120 joules. And the same sort of thing at each of these different temperatures you can compare, right? Comparing iron, a kilogram of iron to a gram of iron, it's just 1,000 times less, right? Because the only thing we're changing is the amount of the material, or the amount of atoms that's there. It's the same material, same temperature, just 1,000 times less of that, of those atoms. But water is a different material entirely, so even if you have the same amount or the same mass at the same temperature, each of those atoms essentially has more energy. There's more energy per atom of H2O than there would be per atom of iron. So, comparing that total internal energy between materials and different amounts of materials, different amounts of the same material, if we look at instead the average internal energy, so the average amount of energy per atom, that is what essentially is a measure of temperature. So it depends on the temperature, and it depends on the material, what kind of material it is. Water, H2O versus iron versus gold versus methane versus all. The type of material is very important, right? So for instance, if we compare, again comparing water, a kilogram of water at 300 degrees Kelvin, average internal energy is 36 joules. However, if you look carefully at these tables, each of these tables, their average internal energy is multiplied times 10 to the minus 21st, which is about a billion trillionth of a joule. So for the average internal energy, remember, this is saying on average how much energy does one atom have, right? And each atom has very little energy by itself. The thing is, there's so many atoms that come together to make a material that all together that can amount to quite a lot of energy. So back to comparing, so you have that water at 300 degrees Kelvin, 36 times 10 to the minus 21st joules, average energy, versus you have a kilogram of iron, also at 300 degrees Kelvin, 11 joules, 11 times 10 to the minus 21st joules is the average energy per iron atom. So less energy per atom in general for iron to water. However, when we look at a large mass of iron versus a small mass of iron, the average internal energy doesn't care how much material is there. It's just how much per atom individually. So at the same temperature, 300 degrees Kelvin, the iron in that 1 gram and the iron in that kilogram have the same internal energy, right? And at all these temperatures, 11 times 10 to the minus 21st joules. So if we're thinking about average internal energy, only care about, or only matters what the temperature and the type of material is. Right, so if average internal energy is it's essentially the temperature of an object, how do we change that? How does that change? Right? So essentially, at a basic level, you can say that we can increase the internal energy of, and therefore the temperature of an object by tapping some sort of energy source. And we'll get into more detail what that means, but just some examples, if you have a fire burning, this is a source of chemical energy, and that energy being released can cause the internal energy of other objects near it to increase. You can up the internal energy. It turns out friction can also produce energy, so that's why if you rub your hands together, there's a frictional force between your hands that's opposing their motion, and that frictional force actually can, essentially it can be a source of energy to increase the internal energy of the atoms in your hand. Right? So that's why the temperature of your hands will raise, at least the front of your hands, more directly, will rise as you rub them together. And another example would be like an electric burner, where this is essentially electrical energy that essentially heats up the burner, and you can actually transfer energy to an object, and again, you increase its internal energy, you increase its temperature. So before we go more into heat and internal energy and how heat and internal energy and temperature are all related, it's worth pointing out that adding the same amount of energy to two different materials is not going to have the same effect of changing their temperature, of increasing their average internal energy in the same way, right? Materials are different, they act different. So, as an analogy, you might think of, an analogy for how much energy, internal energy and temperature, energy in terms of energy added to a substance and the temperature change of that substance. You might think of as an analogy to the amount of money that a person has and how much happiness, or how happy they are. Right? So, some people need a lot of money to be happy. Right? Some people don't. That's just people. Right? People are different. So in the same way, some materials need a lot of energy in order to increase their temperature, or change their temperature. Right? Water is an example of one of those. Water needs a lot of energy, so in the analogy, you would need water to be a lot of money in order to be happy. Right? Water needs a lot of energy in order to change its temperature. Other materials would be on sort of the opposite end, like iron. Iron does not need much energy in order to change its temperature. Right? So, yeah. Okay, so I mentioned this term heat, and now I want to be a little bit more precise what I mean by heat. So, heat is essentially, heat is internal energy in transit. It's internal energy in motion. It's energy going from one material to another material. So the internal energy transferred from one thing to another. So in that sense, heat is just energy. It's a kind of form of energy in a way, right? It's just specifically it's energy when energy transfers from one material to another. So how does heat flow? Well, in general, heat will always flow from a higher temperature object to a lower temperature object. So at least spontaneously or naturally, heat always flows from that higher to that lower temperature. And that is to say also that heat's going to spontaneously flow from that high temperature object to the low temperature object until they come to the same temperature overall. Then there's no difference in temperature, there will be no heat flow, right? That is what we call, those objects would then be in thermal equilibrium, they're at the same temperature. So one way to imagine or to think about heat and how heat flow is in terms of our atomic picture, right? So if you keep in mind that a hot object, high temperature object, again has the atoms that make up that object are moving a lot more. They're moving quite a bit, right? So you could imagine maybe a very hot piece of iron and a cold piece of iron. Right? In the hot iron, all the iron atoms are jiggling around a whole bunch more than the ones that are in the cold piece of iron. Right? Then if we take these two pieces and we put them together, kind of touch them up on their surfaces, then what's going to happen is all the hot iron atoms, at least on the surface here, are going to start knocking into the atoms that are in the cold piece of iron. Right? And knocking into them, these are collisions that are happening. So they're transferring momentum to all the atoms that are in the iron atoms in the cold piece of iron. Right? So they're giving some of their energy in that way, transferring all that momentum to the other atoms, and so that slowly and steadily increases the amount of motion in the cold piece of iron. Right? And that process sort of happens throughout the material, on both the material, like all that the heat is going towards the lower temperature material till eventually they're essentially, on average, all the atoms are moving the same amount, and so some collisions happen to transfer a little bit of energy that way, but other collisions happen to transfer energy that way, and it averages out, and that's when there's no more difference in temperature, so they're at thermal equilibrium. Alright, so as a check, a heat check, if you have, say, a red hot thumbtack, say somehow you put a thumbtack, I don't know, in a fire for a while, it got red hot, grabbed it with some tongs and you immersed it in a cup of warm water, what direction will the heat flow be? Or the direction heat will be from water to the thumbtack to the water, no heat flow, or we don't know. So take a second, what do you think? Alright, well hopefully you said heat is going to flow from the red hot thumbtack to the warm water. So it has nothing to do with how much material there is. There might be way more warm water than there is volume-wise than there is the thumbtack, but the fact that that thumbtack is at a much higher temperature than the water means that heat is going to naturally flow from the thumbtack into the water. Until eventually the thumbtack and the water are at the same temperature. So how do we measure heat? The quantity, or how do we say how much heat, the amount of heat there is, the amount of energy that transfers from one place to another, one object to another? Well, again, remember, heat is just a flow of energy, and being energy, we measure it in joules. Energy, joules is how we measure the unit for energy. So we measure it in joules, or an equivalent unit, another kind of way of measuring energy, just like feet is another way of measuring distance as inches is or miles is. So another way of measuring energy is calories. And essentially a calorie is about 4 joules. It's a little over 4 joules. So it's the same measurements or same things we're measuring, we're just measuring energy. It's just calorie, came up with a calorie because, well, it makes more sense in terms of how we measure temperature changes in some places. specifically, it takes 1 calorie of heat in order to change the temperature of 1 gram of water 1 degree Celsius. So this is sort of where the definition of calorie, the amount of energy a calorie is. So a caveat to talking about energy in terms of calories is it sucks because we are very familiar with the term calorie, but it's not used in the same way in, say, food labeling. So a food calorie is 1,000 calories. So technically, a calorie on a box of cereal or something like that is that, when it says a calorie, what it's really saying, scientifically, specifically speaking, is 1,000 calories, a kilocalorie. So this is rather confusing, but that is what it is. There's not really much else I can tell you about that, except that it's kind of annoying. So, in terms of changing the temperature of, say, water, just like 1 gram of water can be changed 1 degree Celsius by 1 calorie of heat. A kilocalorie, 1,000 calories, or a food calorie, 1,000 calories, is enough energy to change the temperature of a kilogram of water by 1 degree Celsius. So it does make a little bit more sense to talk about a kilocalorie in terms of a person, because, again, we're mostly made up of water, so to change the temperature, the internal energy of our bodies is more along the lines of changing like kilograms of material of water versus just a gram. So that might be why, but it's still rather annoying. Alright, so another question for you. So imagine you have 2 different amounts of water. Remember maybe this bucket, the teacup, and you add the same quantity of heat to each of them, right? The same amount of joules, the same amount of calories to each of them. What's going to happen, the temperature of the smaller amount of water, the teacup, versus the bigger amount of water? Alright, hopefully you said that the smaller amount of water, its temperature is going to increase more. So remember, we're adding the same amount of energy essentially to each of these things, and the fact that there's much less water, there's many fewer atoms that make up the teacup, the water in the teacup, than the ones in the bucket, means that each of those atoms is going to get more energy, or going to get a bigger piece of that energy. Versus there's way more atoms in the bucket, each of those atoms is going to essentially get less of a chunk of that energy. So the average internal energy of the water in the teacup is going to increase more than the average internal energy of the water in the bucket. Alright, so now we're going to get to another sort of property of materials. What makes materials, or thing about materials that's different in terms of heat and temperature, has to do with this thing that we call specific heat capacity. And it largely accounts, or gets to, that idea of how some materials need more energy in order to change their temperature than others. Technically the definition for specific heat capacity would be the amount of energy, internal energy, that is required to raise 1 gram of the material by 1 degree of temperature, degree Celsius or degree Kelvin. So that varies depending on materials. Different materials need different amounts of energy in order to change their temperature by the same amount. It also depends on, it varies depending on the state of the material, so whether the material is in a solid, a liquid, or a gas form, its heat capacity is going to be different. And also depends on the pressure. Right? So those are a lot of subtleties. We don't need to worry too much about those. The bigger picture is that this heat capacity is sort of like a thermal inertia, or the thermal inertia of a material. So keeping in mind or recalling that inertia is a measurement of how difficult it is to move a material, to get a material moving, right? And rotational inertia was a measurement of how difficult it is to get an object to rotate. So in this case, thermal inertia, or heat capacity, is a measure of how difficult it is to change a material's temperature. So if an object has a very high heat capacity, it means it's very difficult to change its temperature. It means you need to dump a lot of energy into that object, or take a lot of energy out, in order to change its temperature. So an example in like a real life, I guess, place where this comes into effect is if you say took a piece of pie, crust and filling and all, and didn't wait for it all to cool down very much, but just went ahead and tried to eat some of that pie. Well, what happens? You probably get burned, very likely, if you didn't wait for it to cool down. But in looking at it even closer, it turns out it's not usually going to be the crust that is going to burn you. It's usually the filling. And the reason being is that the filling has a lot of water in it, right? And water has a very high heat capacity, has a very high thermal inertia, meaning that even though the crust and the filling are at the same temperature, in order to bring that temperature down to sort of your internal body temperature so you can actually ingest it better, you need to take heat out of those materials. But since the crust has a much lower heat capacity, it means not a whole lot of heat needs to come out of it before its temperature drops down. Right? So you get some heat coming out of it, but not a whole lot, so that's not not generally enough to burn you. Whereas the filling is a lot of water, and it needs to dump a lot of heat needs to come out of it before its temperature drops down. And that heat's got to go somewhere. It's going into your mouth. It's probably going to burn you. Cool. So these are just some examples of the different heat capacity of some various materials. Okay, so just to get an idea, the actual numbers we don't need to worry about that much. It's really just in comparison. So these are in descending order, where water, liquid H2O, is right there up at the top. Right? Water, like I said, has a very high heat capacity, meaning it's very difficult, or it takes a lot of energy to change water's temperature. Either a lot of energy put in to heat it up, or a lot of energy taken out to cool it down. Ice and steam are not quite as high as water, about maybe half of what water's heat capacity is, but they're still pretty high. Right? And then you get lower and lower: aluminum, iron, all the way down. We got glass down here, copper, mercury, gold. So yeah. So essentially down here at the bottom, like gold and mercury and copper, these are things where you really don't have to add that much heat to these materials in order to increase their temperatures. So let's see an example of this heat capacity in action. So you can do this if you have some isopropyl alcohol or rubbing alcohol, I think usually, rubbing alcohol. And essentially you just make a 1-to-1 solution, 50-50 solution of that rubbing alcohol and water, and you dunk a dollar bill into it, or dunk any piece of paper into it actually, take it back out, don't let it dry off, but try to light it on fire and see what happens. let's see what happens. There is, I think, the isopropyl alcohol. Oh no, that was water. That's the rubbing alcohol. So it probably doesn't need to be that exactly. It's 50-50, but close to 50-50 is probably good. Then go ahead and take your dollar bill. And while we're doing this, try to imagine what's going to happen. Okay. That dollar bill, if you lit it on fire by itself, is going to burn pretty quickly. However, now that it's soaked in that water and the alcohol is very flammable, so the alcohol will burn. But when it's burning, all it's doing, since there's water still soaked around it, all it's doing is dumping heat into the water. Right? And the water has a very high heat capacity, so that heat isn't enough to really change the temperature of the water even a little. He goes and he grabs the bill right afterwards. So when you do this, you essentially burn the alcohol. The heat from that burning mostly goes into the water, barely changes the water's temperature, and never really affects the bill itself. This is also kind of indicates why it's very difficult to light wet wood versus dry wood. Alright, so let's do a couple more questions about specific heat capacity. So say you have a piece of watermelon in a cooler and a sandwich in a cooler, and they're on a hot day. Why might you think that the watermelon will stay cooler for a lot longer than the sandwich will? One question. The other question is, why is it that the climate in the desert is so hot during the day and yet so cold at night? Yeah. Alright, so take a minute, try to write out an answer. This isn't a yes or no question, so try to write out maybe a sentence or so. Nice. Alright, so for the first question, well, watermelon is named such because it's got a lot of water in it, mostly made up of water. And again, water has a very high heat capacity, or specific heat. Same for us, it's the same difference. Specific heat capacity, it's close enough. So essentially, it takes a lot more. The watermelon will absorb a lot more heat from its surroundings and not really change its temperature very much. It won't increase the temperature very much. Versus the sandwich, it's made up partly a decent amount of water, but the bread, the meat, there's other materials, and they have much lower heat capacity. So when they absorb the same amount of heat, the temperature overall will increase more than the watermelon. So what about the desert, right? Why is the desert very hot in the day and very cold at night? Again, it comes down to water. And the desert is classified as such because the desert is very little moisture. There's very little water in general in the desert, in the air, in the ground, but yeah. So for the most part, the desert, is made up of sand and rocks, right? And the sand and rocks, the silicate and whatever other materials that are making up the sand and the rock, they have a much lower heat capacity than water does. So having a very low heat capacity essentially means that during the day, when the sun's out, there's a lot of heat from the sun that's being added to the sand and the rocks. And since they have a low heat capacity, their temperature is much more easily increased by that amount of heat than if it was, say, moist soil or something. So that's why the rocks are going to get very hot, right? Their temperature increases a lot for the same amount of heat. And then on the flip side of that, at night, when the sun goes away, right, there's no more heat being added directly by the sun, but again, that low heat capacity means that the rocks and the sand, now they're going to give off that heat back into the air because the air is cooling down, and they don't have to give off a whole lot of heat before they cool down a lot. That low heat capacity means it's easier to change the temperature. It takes less heat coming out to cool that material down. So, for the same reason as it gets hot, this is why it gets cold. Alright, so one more demo about heat capacity, which is kind of interesting, is that if you take 2 cups, either 2 paper cups, and one you fill with water. Remember, water is very high heat capacity, a lot of energy to increase the temperature, or change the temperature overall. So you take a cup of water, and then you take another cup, paper cup. This picture is with sand. You don't even have to have sand, it could just be an empty cup, or with air in it, right? But it's important that you have one with water and one that has some other material, either air or sand or something like that. Let's see what happens when you try to heat up. So I believe the one on your left is the one that has the water in it. And, I'm sorry, the one on the right, my left here. So that was, I think it was just an empty cup. She didn't have sand, but she had water in the other one. Right? So what we see is the empty cup, or the cup that had air in it, right? It has a lower heat capacity overall, so that the heat coming off of that candle flame can much more easily increase the temperature of that cup, and essentially combustion can happen once that material gets hot enough. So you increase temperature enough, you get the cup actually burning, and it will burn through. Whereas the bottom of the other cup doesn't have a mark on it really, right? So the other cup had water in it, and the candle flame again was heating up the material of the cup, and that material is paper, probably. So it has a pretty low heat capacity. It's will absorb the heat and increase its temperature, but it's also in contact with that water, right? So a lot of that heat is not just sitting in the cup, it's also going into the water. But that water, remember, say it many, many times, that high heat capacity means that the water can absorb a lot of that energy and not really increase its temperature. So the fact also that the water and the cup are in contact means they're going to generally be in thermal equilibrium, so the water's temperature not going up means the cup can't go up. Temperature can't increase very much either. This is why hold the water cup over flame for much longer than you would be able to the empty cup. Alright, so the last sort of topic for this lecture is thermal expansion. Right? Again, having to do with temperature and heat, internal energy. So as I mentioned earlier on, when I first started talking about temperature, when you increase material's temperature, that means you're increasing the sort of the amount of motion that all the atoms have, the average amount of motion that those atoms have. And in general, that motion, the fact they're moving around more, means they need more space. Right? So this is a very kind of straightforward way of understanding why when you heat up a material, when you increase its temperature, that material generally expands. It needs more room because the atoms are all moving around more. The opposite of this is also true. Essentially, if you reduce the temperature of a material, that means all those atoms are all overall, or on average, moving less, so they need less room, so they contract. Right? So increased temperature, objects generally expand. And this is true for gases, liquids, solids, plasma. There are exceptions, but this is the general rule. You increase material's temperature, it expands. You decrease its temperature, it contracts. So in this diagram on the right here, this is just showing you like an atomic sort of picture of a thermometer, where all the atoms in the thermometer are usually a liquid, maybe probably not mercury anymore, maybe some kind of alcohol, where the bulb is the majority of the liquid, and so you put the bulb in some kind of different temperature, or you know, it's sitting outside, the temperature of that material is increasing, and since it's increasing, all the atoms are moving more, and they need more space, and so they expand. So that's why this temperature reading, when it's in a higher temperature area, you have a higher level reading on that thermometer. And that's just shown here as in, you know, sort of actual photograph of a mercury thermometer that is not in hot water, and it's shown at a certain height, versus then you put it in the hot water, the mercury heats up, it expands, and now that height of the thermometer is increased to indicate that it's at a higher temperature. So this has some very real practical consequences. Among other things, engineers or civil engineers, city planners need to account for, and architects in general, need to account for thermal expansion and thermal contraction. Because when you build something like a bridge, the material that the bridge is made out of, whatever it is going to go through a whole range of temperatures. Right? In the midsummer, it's going to be very hot. Middle of winter, it's going to be very cold. So it'll go through a whole range of expanding and contracting, expanding and contracting. And if you don't account for the fact that that material is going to expand, then you get something like that sidewalk picture here, where the material is generally, it's sort of expanding in all directions, and then at some breaking point it kind of pushes into itself, and you have this failure of the material, bursts or cracks. So in order to deal with this, like on bridges, you generally will see these things called expansion joints. It's that kind of weird noise makes you hear generally when you first drive onto a bridge, is because you're rolling over an expansion joint, and that is a place that is specifically designed so that each side of that, on either side of that expansion joint, the material can expand and the joint kind of closes up, or the material can contract and the joint opens up a little bit. But you have accounted for the fact that there will be this expansion and contraction, so that when it does happen, your bridge doesn't collapse, crack, or collapse. Yeah. Alright, so let's just finish up by looking at a couple examples of this. This first one is an example of thermal contraction, where you take these two sort of wands, one with a spear and one with a ring, or a hoop on the end, and they're designed in such a way that at the same temperature, the spear will fit just fine through the hoop. Right? Not a lot of clearance, but it fits just fine. However, if you take the hoop, I think that's what we're doing here. If you say take the hoop and decrease its temperature, then it's going to contract. The material is going to contract, and well, if you cool it down enough, it contracts enough, it's going to be now too small for the sphere to even go through. Right? So we're going to see you dunk this hoop into liquid nitrogen, it cools it down a great bit, or decreases the temperature a great bit, it contracts a lot. You don't really see the contraction with your eye. It's not hard, it's difficult to see. It doesn't actually physically seem to contract a lot, but it does, and you can tell that because you can no longer fit the spear through that hoop. So there you got the spear, you got the hoop. The sphere goes through the hoop just fine, no problem. And then we take some liquid nitrogen, decrease the temperature of the hoop, contract the hoop, and the sphere now no longer fits through. Right? This is thermal contraction, plain and simple. So the last example we'll look at, thermal expansion, thermal contraction, is, if you take, say, something like a glass cup and you heat it up, whatever it means, I don't know, put it in the oven, something like that, put a burner under it, right? Heat it up so that the whole thing ends up getting to the same temperature. It will have expanded, all the material will have expanded, so it got a little bit bigger. And then if you take that cup and cool it down very quickly, you can do that by, say, like putting it into a bucket of ice or ice water. What ends up happening is the outside of that glass, the outside of that cup, is going to cool down first, right? The heat is going directly, coming directly actually out of the outside of the cup, and the inside of the cup it takes a little bit longer for that heat to get to the outside to go to the ice water. So the heat comes directly out of the outside of the cup, and the outside of the cup is going to start contracting, right? It's cooling down, its temperature is going to reduce, it contracts, and if it happens quick enough, then it contracts faster than the inside is contracting, and you end up getting a failure of the material. You get cracks, pops. All right, let's see that. So this was actually with glass marble, and so in order to heat it up, it looks like they're taking a blowtorch, some kind of torch to it, heat it up for a bit. Now it's red hot. We're going to put it in maybe just a cup of cool water. And the cracks actually are forming. It's kind of difficult to see maybe in this video. This would probably be a good one to go and check out on your own. But I think there's a pretty dramatic sort of cracking event at some point. Yeah, you can see all the different cracks that have formed inside of it. Oh, and then it sort of pops. That one might be worth watching with the sound on. I think the sound's pretty satisfying with that. Oh, and then yeah, it kind of exploded. So there you go. That was in this case it was sort of, the same kind of idea. Where you had this this sphere of glass, it was all heated up, so it all expanded a bit. And then you put it into some water, so the heat starts coming out of the outside of the marble first, and so the outside contracts, and essentially then you get to the breaking point where it's putting so much pressure on the inside of the sphere that hasn't contracted yet that you actually just start breaking that material. And that's it. That's all I got for this lecture on temperature and heat and thermal expansion. Hopefully you get a better understanding of temperature and why all these topics very nicely sort of mesh together. I think the next lecture is about heat transfer. So we talked about heat and the fact that heat is a flow of energy between objects at different temperatures. And the next lecture is going to go into a lot more detail about the different ways that heat transfers. So there are a number of different ways that heat will transfer from one material to another. But that's it for now. So have a good day, and I'll see you around.